We are going to look at the energy changes in the photoelectric effect now. And from the previous lesson, you will remember that electrons are bound to the atom, and the valence electrons, the outside electrons, could gain enough energy from some source, it could be heat or anywhere, can gain enough energy to leave this metal. So it could be emitted from the surface of this metal if it gets enough energy. And in the photoelectric effect, we give the metal energy in the form of radiation. So we are going to shine an electromagnetic wave onto this metal to give the metal energy. Now let's make up a very creative metal, and we can call it metal M. And those electrons in metal M, let's say they need 100 joules of energy to be emitted. So if they are sitting there on the outside of the atom, and there's the nucleus attracting them, those electrons need 100 joules of energy to be emitted. That means they just then free. They're just sitting there on the outside of the atom. Now, we gave a specific name to this energy, and I want you all to say it as a choir. What do we call the energy that the electron needs to be emitted from the surface of the metal? And there's already a hint on the board. So 1, 2, 3. I hope you all shouted work function. So the work function is the energy that the electron needs to be emitted. So we say it's the work function of the metal because it's specific to every single metal. Now, if we say the red light that we're shining onto this metal contains photons that has an energy of 80 joules. Now remember, E is equal to HF still. So we can work out the energy and we can work out the frequency if we have the energy. So either one of those two are normally given to you, or they can give you the wavelength. And then remember, you can use E equals hc over lambda as well. But now these little photons that we've spoken about are particles, and they are hitting the electrons. And all their energy, their whole 80 joules, will be transferred onto that electron. But the electron needs 100 joules to be emitted. So now it doesn't matter if I send 1,000 of those 80 joules electrons, and I can also, photons onto this metal. It's not going to send out one of those electrons because those electrons need 100 joules. So they need a packet of energy with 100 joules, and the red light is only giving them 80. Please remember intensity of the light, or a brighter light. Brighter was connected to power, remember, in electricity. And power is energy over time, or work over time. So in a specific time, a certain amount of photons will hit. And if I make the light brighter, it just means more photons are hitting. But they still only have 80 joules of energy. So they do not have enough energy to send out any electron. So you will see no electrons being emitted. And we'll do some experiments on this in early next week. So now if I move on and I say, let's say the green photons gives us exactly 100 joules. So again, I can use that energy to get the frequency, or if I have the frequency, I can use that to get the energy. And these green photons are now hitting the metal. So they're hitting electrons. Those electrons still need 100 joules. So they're getting exactly 100 joules. So they have enough energy to go and sit there on the surface of the metal. And that's what they'll do. They'll be emitted, but they're just going to be sitting there. So the only way you can get them to move is, and you'll see that in the PhET simulation, if you connect a positive charge close to them, then they will move to a positive charge. Electrons will always move towards something that is positively charged. But it's not going to move on its own. So now remember, this energy, if the energy is exactly what the electron needs, we call that energy the work function. But now if I look at the light, this green light is also special because this green light had the exact energy, which means the exact frequency at which electrons will be emitted. And that brings us to our other important definition, because the work function, remember, is related to the threshold frequency, also by Planck's constant. So now this light, the green light, has exactly the threshold frequency. Anything lower than that frequency will give us a lower energy, which means no electrons will be emitted. And anything equal or higher than that will give us enough energy to emit electrons. Now we're going to look at those blue photons. So the blue photons hit the metal, and let's give them an energy of 160 joules. So here they come, one by one, they hit electrons, and their energy can also be calculated using E equals hf. But now, those electrons are still the electrons of the same metal, so how much energy do they need to be emitted? Correct, 100 joules as well. So they are going to absorb those 100 joules so that they can go and sit on the surface of the metal, but now they have extra energy. They have an extra 160 joules. So they sit now there on the surface with their 100 joules, but now the extra energy, the extra 60 joules of energy, is still in the electron, because remember the whole packet, the whole 160 joule packet, photon energy gets transferred onto that electron. And that electron now has 60 joules extra. So those 60 joules of energy that the electrons now have, they can use to leave this metal with. And remember, the energy of something moving, is called kinetic energy. And you can also calculate the kinetic energy using half mv squared. So now we're ready to put this all into one equation. If you understand them separately like this, then you'll understand how to use the equation and change the equation to what you want. So we started with light. Light has photons, and we started with the energy of the photons. The photon energy is converted into, the whole packet of photon energy gets absorbed by the electron. Now it needs some of that energy to just be emitted, and you should be able to all shout out that that energy is called the work function. But now the electron has some extra energy, and that extra energy is the kinetic energy. Now, they're not always going to give you the energy of the photon. They might give you the wavelength of the photon, but you can convert energy into wavelength into energy, because you know from your information sheet that E is equal to hc over lambda. Sometimes they might give you the frequency, but you also know that E is equal to hf. So according to what the question tells you, you're going to change this equation. The next thing is that you need to remember that the work function energy is the same as the minimum energy of the light, which is equal to hf naught, which is the threshold frequency. So you could also change the work function energy to hf naught. So they might give you the threshold frequency, or they might ask you for the threshold frequency, and then you'll just change it into that. The last energy then that is left, so the energy of the photon, some of it is absorbed as the work function, and the rest is left for the electron to move away with. And that's the kinetic energy. And you know that kinetic energy is just half mv squared. So you could just put half mv squared in the EK calculation, because often they ask you for the actual speed of the electron. How fast are these electrons moving away? So what we're going to do now is actually look at your textbook for the first time. So in your notes, we are now already on page 214, and we're ready to do example 3 to example 6. So that's I'm going to leave for you to do for this lesson. So example 3, 4, 5, and 6. And 7 I'm going to leave for now, because I want to look at the graph in a little bit more detail and explain to you what goes on there, because we need to use y equals mx plus c again, you so love. So I'm going to stop here, and I would like you to then go and do example 3, 4, 5, and 6.